Hello everybody! I hope everyone's having a wonderful day. So today we're going to be proving another property of big O. It's called the product rule of big O. So the statement of this is going to look a little complicated at first, but I assure you it's actually quite simple. And at first it will also look like something a little bit strange, or you might ask, Dan, what does this have to do with me analyzing algorithms? And I'll explain in a moment. So the statement of the theorem is if F1 is big O of G1, and F2 is big O of G2, then it must be that the product of F1 and F2 is big O of the product of G1 and G2. So just to motivate why exactly you might be interested in this property is very much the case when we have an algorithm that has a so-called nested loop. So for example, you might have a for loop embedded with another for loop. You may count the number of times an inner loop iterates, or the amount of work that occurs, or number of operations that happen within that loop. This may be, for example, F2, and F1 may, for example, be the amount of operations that occur on the outermost loop. So this would be, say, the number of iterations of the outermost loop. That would be most likely what F1 would be. So what this statement is that if you know that F1 is big O of G1, and you know F2 is big O of G2, then the result will actually be the product of those two resulting functions. Seems pretty straightforward, right? So this, you can encounter this and use this when it comes to nested loops. Just be very careful when you're counting. Sometimes you don't necessarily need this property at your disposal. It's just something nice to know. So anyways, let's prove this statement. So what do we usually do when we prove statements like this? I give you a game plan. So some rules that I'm going to follow. So that way I communicate clearly to the reader what exactly I'm trying to do. So I'm going to say, in order to prove the claim, we find constants. We find constants C, which is a positive real number, and N0, which is in fact what? It's a positive integer, right? It's a positive integer. Such that for all n greater or equal to N0, for all n greater or equal to N0, it must be that F1 of n times F2 of n is less than or equal to C times G1 of n times G2 of n. Right? So now, this is where in our proof we would like to use things we know in advance based on the conditional. So we know if we want to show, given these two facts, this follows. So we're going to use these two facts that I have right here. And what are those facts? What are those two facts? They are, in fact, that we have two big O statements. So I'm going to use them in a definition. I'm going to invoke both in the same sentence. So just read what I write down here very carefully. So what am I going to do? If F1 is big O of G1 and F2 is big O of G2, then by the definition of big O, what can we say from the definition of big O? That there exists constants for each one of these two statements. These two I've just stated right here. There's constants that exist. So I'm going to list those out such that certain inequalities hold, right? By the definition of big O, there exists constants C1 and C2. I'm just giving them names. These are positive real constants, right? One for each invocation of the definition of big O. And N1 and 2, which are going to be positive integers, such that that both the following things are true for such a statement. So what did each one of these actually say? So let's think about that. That f1 of n is less than or equal to c1 times g1 of n. And this is true for all n greater or equal to 1, right? And f2 of n is less than or equal to c2 times g2 of n for all n greater or equal. Is it 1? No. This is n1 here, right? Got to be very careful. It's n1 and n2, like this. Why? Because that's from the definition of big O, right? We need to make sure we're invoking the definition correctly. So these are the two facts I have at my disposal. Period. Now let me change it up. Comma. Such that both this are true. See, it's way more fun. It's way more fun. Now, I'm going to select N0 in advance. It makes me writing out these inequalities a little easier. So watch this carefully. Then by selecting N0 is equal to the max of N1 and N2. We did this trick, by the way, before. Observe that by multiplying over the two inequalities for all n greater or equal to n0. This part right here is really important because it's me telling you for which this statement is in fact true. So I'm going to multiply over these two inequalities I have up here. So what should that end up being? It should be f1 of n times f2 of n, which is going to be less than or equal to c1 times g1 of n times c2 times g2 of n. But what's this? I can rearrange these terms through associativity, right? Basically, I could permute these elements because they're all being multiplied. So I end up with c1 times c2 times g1 of n times g2 of n. Do you see what I should select for c? What should I select for c? What should c be? It should be this, right? Because you'll notice that this actually gets me to where I need to be. So I'm going to pick c to be the product of c1 and c2. So choose c is equal to c1 times c2. Therefore, we're done, right? Therefore, by the definition of big O, then we know that f1 times f2 is in fact big O of g1 times g2. And we're done. Boom. So you see how I can use some of the strategies that I've done in the past to derive in a really nice simple way my proof. Anyways, that's all I have to say about the product rule. Like I said, the proof is nice and straightforward once you see some of the tricks that we've been doing over the last several different properties that we've seen so far. So that being said, I want to say thank you very much and have yourself a beautiful day. I'll see you later.